Okay, so with that, I think keeping in the line of thought of what has been discussed during the entire day, I would like to focus on one problem that that we had attempted to look at with respect to photovoltaic effect, and Satish had alluded to in the morning talk of how to design polymeric backbones to generate charges. And one of the things that came up in discussion after that also was the nature of excitons in systems where you have a very delocalized electronic structure, how these electrons that are delocalized across bigger backbones, not just very short segments of a monomer, how do they interact, and how easy is it to split up these excitons into free charges, considering we are working in organic systems, right? And Ravi mentioned it's all insulators with very high, very low dielectric constant. So how do I take out charges, right? So that's one of the big problems in molecular materials, and that I would like to keep that in focus before I delve into the results of how exciton diffusion can be used to do solution nanoscopy. Okay, so before I go into that, let me actually just frame the problem for the audience that is mixed, quite mixed. One of the things that I take home from what Michael Gretzel's phenomenal work in 1991 presented was the fact that people could couple, or scientists could couple, molecules to semiconductors, and via this very subtle trick, they can use the molecular absorption to do current, flow charges through a semiconductor with a completely different action spectrum, right? The semiconductor action spectrum is essentially nothing but anything higher than the band gap. And those can be modulated, of course, by band gap engineering of the semiconductors. But what the molecule gives you is an additional framework to tune that action spectrum to the visible, to the near IR. Okay? And well, this is something that one has to appreciate in this framework of using a TiO2, a nanoporous TiO2, and coat it with molecules on top. And this, of course, went into different directions and dimensions in photovoltaic community, to the point that people have now come up exactly measuring, because there were problems in appreciating the efficiencies, and people had to understand how these molecules are now coated on the surface, whether the charge transfer rates and the electron transfer rates are, do they depend on the orientation of how they are bound. So those led to this nice experiments that Latha is going to describe in the public lecture, where now fundamentally you are asking the question how you can use molecules as a conduit for charge, okay, and between two electrodes. So this subtle feature is often missed in the big hype of dye-sensitized solar cells, but you have to think that actually Gretzel could not have made this successful using purely a molecular system. If it were not for the TiO2 band of states, it would have been so hard to put the charge across and move it to generate a current in an efficient manner, because the mobilities, the molecular materials have challenged mobilities. The mobilities are not very high, right? So this comes back to this fundamental question that has bothered chemists specifically, who would like to, do artificial photosynthesis in lab. They have been fundamentally challenged by the fact that even after having a very fast charge transfer, it's something that Mahesh pointed out in an earlier talk, that even if you do a light-induced charge transfer, which could be ultra-fast, you do not make use of these charges unless you separate them, unless you block them from recombination. Okay? And one of the fundamental problems with these systems is the charges are very strong. If they are nearby each other, if these two molecules are very close, they have a very high propensity, because of the large binding energy, that they will, of course, collapse and recombine within few picoseconds, unless you do tricks like Mahesh showed in the morning, where you can stack it up in organic systems and play the game of how to delocalize those naked charges, which are an electron and a hole. Okay. The other problem that comes into in a big way is even before the charge transfer, even before that, right? The charge transfer is occurring at an interface. I call it as an interface because it's an interface of a donor and acceptor. Okay. It could have been at the interface of a molecule and a semiconductor, molecule or a metal. Okay. Even before that, the problems arise because these are molecular materials. The excitations are strongly bound. The electron and hole have very strong interaction because there are really localized states. So the binding energies are high, very low dielectric constant, as opposed to the materials, Eilert described in silicon, where you get free charges almost instantaneously at room temperature, unless you go to lower temperature where you still have bound excitons. Okay, so these are some of the issues that you have to deal with when you think of molecules as the next generation substitute for other kinds of metal semiconductor, metal insulator contacts. Okay, so the challenges for the chemist is pretty clear, and I'm pretty sure Satish and Mahesh always think about this, that you have to generate new materials with large absorption cross-section. You have, of course, to have the tunability in the architecture to change the energy levels. And there is something new that is coming up in the community is you don't always have to move charges. You can move energy. That is, excitation energy can flow through excitonic transports. Of course, this fundamental thing is true that you have to generate new materials, but also now with physicists and engineers coming into the community, it is clear that engineering interfaces of a molecule with a semiconductor through thinking about chemical interactions that Eilert pointed out, through hybridization of atoms on the surface, and other sorts of interfacial charge transfer effects, you need to think about very carefully while you are engineering the interfaces. And of course, if you can go beyond the linear regime, that means with every photon, if you can produce 2 excitons, that's fundamentally new in the absorption process. And people are, there were some examples at least of singlet fission, where people have gone from a higher excited singlet state to a low-lying triplet, and you generate 2 triplets instead of 1. Okay, so this idea of getting 2 workable excitons from 1 photon just magnifies the quantum efficiency of your process. So you see this in photosynthesis in terms of the idea of photoinduced charge generation. I'm not going to spend too much time. You also see, both charge transfer in photosynthesis in a very nice manner, illustrative of how photosynthesis works by pre-organizing the chromophores. But as I said, it is important to also consider the dynamic effects of this pre-organization, which experimentally people have only come to terms with now, with beautiful experiments coming up from labs where people are looking at using coherent spectroscopy, looking at vibrational modulation of charge transfer rates. But also there are examples in photosynthesis where exciton transport is used to take energy from a very far away light harvesting complex to an interface where charge separation can take place. Okay? Most of my talk will be concerned about materials from the organic systems which look like extended systems. So this is essentially conjugated polymers, and they have a very nice tunability in their backbone. Satish illustrated very nicely today. You can get different colors. That means the band gap, you can tune the band gap. And what is very, very nice about these systems, that you can organize them well, then the pi way, as Ravi alluded today in DNA, you can probably engineer a pi way in these through the pi band of states in systems. Okay. So the ideas have been very simple and developed by Alan Heeger and Richard Friend in their in early 90s and late 90s, when they said that you don't really have to think of the architecture, but if you take just about 2 different kinds of materials that would phase segregate in some way, you can create these interpenetrating layers of donor-acceptor. So in the morning, you saw very nice architectures being developed. But here is the guy who says that, I don't care. You just mix these two, and if you can generate these interpenetrating domains, that is a very cheap way of making a photovoltaic, to generate charges by just, putting in broad sunlight. Well, it was such a remarkable sort of, I would say, discovery that people are still trying to appreciate what happened. Because after 15 years, people are still trying to modulate different kinds of parameters in the bulk heterojunction community to understand this simple process of exciton transport to an interface, charge generation, and then taking our extraction of charges near the electrodes. Okay? So this is still a matter of, there's a lot of specific points that people are trying to address in this, but it is important to appreciate the simplicity of the design. You just have to take two materials in a solvent, throw it on a ITO surface, spin coat it, or whatever way you want to cast it, and you get very nice photovoltaic effect. Of course, there are different kinds of polymeric systems that you can use. With band gap, the problem typically, traditionally, is that as you decrease the band gap, that means you go to more and more, you trap in more and more visible photons, you start decreasing the exciton lifetime. And that limits the sizes of domains that you want in these interpenetrating junctions, and you really want to be in the limit of the exciton lifetime, because the exciton has to diffuse. So that diffusivity, or the coefficient of diffusion, has to be critically understood in all these materials, as well as in context of the lifetime. Okay? So one of the things that bothered us for quite some time in the group is what dictates the morphology of these materials. Let me phrase the problem and come back to you. What dictates the morphology of the eventual film that Heeger and Richard Friend developed as a fascinating magical potion to generate charges. So it has been known, long known, as I stated it clearly, that you have to go through the solvent phase. It's a wet method. So is there a connection between what is existing in solution, and is there an effect of what kind of solvent you choose on the final morphology of the films that you generate? And Satish nicely showed, yes, indeed, solvents do matter from where you generate the films, because the way the polymers aggregate ultimately in the film is very much dictated by their conformational flexibility in the solution, okay, and the propensities. Yes? Lifetime, why does it decrease? So there are multiple reasons for this, but in general, there is a power law dependence in physics. What people say is, if you have a band gap engineering done on your semiconductor or any kind of soft material, you would increase the non-radiative channel considerably as a function of the band gap. Okay? So when the band gap goes down, more and more non-radiative channels come into existence. The manifestation of this is coming from the fact that you have two different molecules in there, okay? And the degrees of freedom that you have, the torsional degrees of freedom, really affect the system. Yeah. No, so the conjugation, so this is a general, this is a general observation. The conjugation length, effective conjugation length of conjugated polymers are usually 4 to 6 monomer units, okay? Now, it is not infinite that you can go to a completely linear chain of the molecule for 10 mer or 15 mer. The problem is, most of the conjugated polymers, if you look at the literature, this is an observational thing. I don't have a specific theory to explain this, but it is generally recognized that your conjugation length is very much dependent on the degree of the conformational flexibility you have on your backbone. And that changes when you start adding multiple chromophoric units inside the same backbone. You could have the same chromophores, okay, the same chromophores, you might have one kind of dependency, okay? But once you start doing that, of course, these are apples and oranges, right? You cannot directly compare in terms of the degrees of freedom. But the fact that you see adding components and pushing your wave, as Satish was telling, pushing it more towards near IR, there is a problem intrinsically, because you add different degrees of freedom which were not relevant initially, okay? No, no, no. You can have donor-acceptor systems which have long lifetime. So that's not the case, but what I'm trying to say is a general trend that you observe, okay? Of course, exceptions prove sort of the rule. But so here is this question that we really were honing in as to what is it in the solvent that really ensures that the morphology of the film is getting dictated. So there had been quite a bit of work previously by different groups in the world who had the same question in mind, that in the dilute conditions with solvent, polymers could be unstructured, but as you evaporate the solvent, there could be some local ordering, which can be picked up through X-ray diffraction, okay? If you could do in situ X-ray diffraction in some way, and this was done with grazing incidence angles, so you could pick up the order in the polymeric backbone as it nucleates and grows into a film. There were other studies and other work that really looked at this problem from a thermodynamic point of view, as very nice paper by Janssen. I think you guys should all read this by René Janssen, where he showed that there exists a phase, an intermediate phase, as the drying is going on, where the polymer domain and the fullerene domain, which is the acceptor, they phase segregate, okay? And once the complete drying happens, the solvent just goes away, but retaining the intrinsic nuclear seed that was there, okay? So the question was, can you experimentally identify this phase, okay? So one of the things that we knew we had a handle on was, if by chance we could, and if as experimentalists, we could measure exciton diffusion timescales, and if we could see the rise of the charges in our experiment in solution phase, under those conditions, in these nano-aggregates that are seeds for the final film morphology, I can talk about length scales, okay? Because exciton diffusion gives you length scale if you know how long it is to generate charges. Because this is the rate determining step of charge generation, the diffusion, and then instantaneous charge generation. So one of the things that was known in the community was, using a simple diffusion model, you can talk about length scales of these nano-aggregates. So what was required was somehow track the exciton diffusion dynamics, as well as the rise of the polarons in the mixed system, okay? So of course, in the lab, we have developed setups where we can look at transient absorption signals. This is a very nice signature of carotenoid molecules, where you can monitor all different kinds of states that exist in specific carotenoids. There's work done by Vijay who's in the audience. But we can also look at transient Raman signatures, where you can look at how the ground state polymer looks like, and in the excited state, what are the features? What are the changes? Because Mahesh mentioned in a very nice talk at the end that he knows that X-ray crystallography shows a bent orientation for his donor-acceptor system, but when it goes to the excited state, who knows what is going on with the nuclear dynamics, because you pushed in so much energy, so you can put in energy in torsional coordinates. So this becomes a very important tool to look at, okay? So so Palash in the group actually started looking at this, and what he found was that it's easy to get hold of P3HT because it's commercially available, and fullerene is also commercially available. Of course, we have the support of Satish Patil to get us other exotic polymers, but we started with this one, and we found a very nice features in specific solvent like toluene, we could see this very nice aggregate feature coming up, okay, at high concentrations. And we could also convince ourselves that indeed, when PCBM is put in the solvent, there is a shift of the PCBM features because of interaction with the polymer. And this is the first report of any such kind, because nobody believes that in solution, polymer and fullerenes have interfaces. But we believe that if you look at high concentrations, you can figure out these interactions. These were done with stimulated Raman setup. It's not possible in regular Raman because fluorescence kills you. You cannot detect anything with P3HT. Okay, so this particular experiment, we asked the question, now if I go and hit the local excited state of P3HT, what would we see when you have the fullerene versus in absence of fullerene? So this is a well-studied system. It's nothing new. You see the transient, nice transient features. There is a red shift because you can clearly see the red shift here. These traces are broken up. This is wavelength axis. This is time axis. And now we have put this in the two-dimensional format, where this is wavelength, this is transient absorption. And you can see the time scales and the shift. There is a very clear red shift that talks about exciton relaxation, when there is energy transfer within the chains, okay? And this has been explained well by variety of photophysicists in the community, especially Greg Scholes. Now, what was clear to us that these time scales are 200 to 400 picoseconds for the exciton lifetime. So do we see, within that lifetime, do we see charge generation? That's the question, right? So we added PCBM, and we see that there are these very nice features coming up when PCBM is added at similar time scales of the exciton. So you see, we have captured a spot where the exciton is relaxing, but along with that, you have additional features on the excitonic feature. When you took a different spectrum, and this was done really carefully because you have to do multiple experiments the same day, you took a delta A spectrum, you could see that the PCBM anion radical features could be seen clearly at 1030, and you could also compare it to the polaron features in P3HT. So this was clear that within the first picosecond, we are generating charges. We could plot all the delta A spectra, and you can see the rise of these charges, which is in biphasic nature. You have a fast rise and a slow rise. So this biphasic nature actually tells us that there are at least two pathways, or by two processes, we can generate charges, okay? So there was a very well-developed model within the polymer solar cell community with photophysicists had developed that in films, you have these domains, interpenetrating domains, and there could be two such ways of generating charges. One is the ultrafast component. When you have the excitation localized near the interface, it's around 100 femtoseconds. And the second could be the diffusive part, where the exciton has to move across an entire domain and charge separate. So we use the same kind of idea to explain our results. It turns out that if you see the slow component, that is the diffusive component, goes from all the way from 5 picoseconds to around 18 picoseconds in different solvents. So there's a strong solvent dependence there from chlorobenzene, chloroform, toluene. Just remember, the rotational orientation times of these solvents do not match with the time scales. So this is not just pure electron transfer. Electron transfer in a regular solvent condition would depend on the rotational correlation times of the solvent itself, because then it will be right for the electron transfer to take place through the solvent. So this is not through the solvent. And the other thing that we saw was almost invariance in the fast component, which is immediate, okay? So when we wanted to now analyze the slow part, we asked the question, can we measure the diffusion coefficient in these solvents? And Palash did an experiment where he did generation of multiple excitons. That is, you give too much power, oversaturation regime, you create multiple excitons in the same nanoscopic spot, and you let them annihilate. Since it's a bimolecular quenching process, diffusion will be integral to this quenching rate. So if you were to calculate that now based on a simple model, kinetic model, you can calculate the diffusion coefficient. It turns out that this is highly dependent the diffusion coefficient is highly dependent on the solvent that we chose, okay? You can clearly see they don't fit the regular model, especially toluene. We couldn't get to a fit which could be explained by the simple diffusion motion. So, but we could find out that there are clear differences in the numbers. Once the numbers were obtained, we could use the simple, simple equation where the diffusion coefficient is multiplied by the rise time, and you can get the length scale. So chlorobenzene showed 0.8 nanometer length scale domains of the polymer, while chloroform around 1.5 nanometers, where toluene showed 2.1 nanometers. All of this is not possible with a regular EM image, okay? It's just impossible to image that with so many carbons, okay? So there is a way, essentially, to look at these domain sizes now in solution. Sorry, this is now published. It's a little bit old now. But the idea is simple. If you could translate these into films, we could see that the ratio is very similar for the nano domain widths. All of these become fiber, but the widths have these ratios that are very similar to this, the domain sizes that we measured in solution. We also got some support while we were doing these measurements through coarse grain simulations, which showed that toluene indeed forms bigger domains of polymer versus bromobenzene, although not chlorobenzene, but bromobenzene has very similar kind of fine domain sizes. So what we actually proposed then was that this is really an evidence for the ternary phase, because we can see solvent dependence to the rise of the charges. Otherwise, so this phase is not the one that is initial in acute conditions, because you don't have interactions. So while you are doing that, you already establish, you go through this thermodynamic minima, and then you essentially push it to drying. So the take-home message is, you can, if I were to understand the molecular interaction between the polymer and the solvent, if I appreciate that, I can design mutant polymers which have smaller length scale to tune the grain size of the ultimate BHJ morphology. So that is something that I think we would like to go into. We would like to use Raman spectroscopy as a way to understand this better. That's something that we would really push towards. But it also tells you that chemists have a huge role to play here, and Friend's idea of just mixing the two things is not the last thing or the last word. You can control morphology if you are clever enough to understand the molecular interactions. So, that is something that I would like to conclude with. I just want to, if I have 2 minutes, I have 1 minute. I'll just like to say that there are other interesting things in the lab that we are pursuing in terms of this exciton generation, conjugated polymers. One of the questions that Satish and I are baffled by is spectroscopic signatures of a delocalized exciton versus charges which are strongly coupled. And this is not an easy problem to work on. You can generate data in transient absorption, but it's very hard to pick up. I know SPD analysis can be done. We also do that. But it's very hard to assign these states, whether they are really polaronic nature, whether radical, which are separated by some distance. So it's very difficult. So instead of that, what we are looking now into using stimulated Raman spectroscopy, we have decreased we have sort of increased the energy resolution. So whatever spectroscopic signatures we want to see is not electronic spectra, but vibrational spectra, and those will be much more resolved. Now we can look at these systems with stimulated Raman spectroscopy. We can pump them, we can bleach these bands, and we can get information on time-evolving structure on the excited states. And you can clearly see just one glaring intensity change. You see this 1230 mode is a very localized thiophene in-plane CH in-plane wagging motion with some C double bond C. It clearly gets enormously enhanced in the excited state as compared to the original parent C double bond C, telling us clearly that exciton localization on thiophene rings become important in the excited state. When you plan to build these kinds of structures that Satish is building with respect to the bridge. So the bridge becomes a very important part in these systems. So the idea, the vision that we have is we want to look at these ideas of excitons and polarons and look at how varying the side chains, we can pack these donor acceptors in different geometries and change the amount of charges that we can build in. I'm not going to spend too much time. This is something that we have recently come, but I would like to summarize. Essentially, the group looks at these phenomena where delocalized excitons and electrons are coupled to the nuclear backbone. And Ajay, who recently graduated, looked into those systems with anthraquinone frameworks, and also looked at the heterogeneity issue of polymers from a spin-casted solution on, say, TiO2 semiconductors that you can make films out of. But this is at the fast time scale. We are also very inclined biologically, especially with Vijay Lakshmi and Joel's work, where we are looking at essentially electron transfer triggered enzymatic action, and especially for enzymatic action on large substrates, conjugated substrates, okay? And please go to Vijay Lakshmi's poster. She has some very interesting data on even the photophysics of these systems leading to isomerization, okay? And lastly, but not the least, we would like to combine these two ideas to do photocatalysis in chemistry. And we came up with this novel idea where you can use charge transfer states to actually break a bond strong enough, like an OH bond, okay? So, of course, there are new additions to the group, and Shritama is actually participating in this meeting. And I would like to thank a bunch of people who always support me with all sorts of help, from materials to, I would say, equipments, to even moral support. There's a lot of support required when you are starting up a new lab, and all of these folks have really, Deepa is here, all of these folks have really helped me. Of course, Ravi has been an amazing colleague as well. So, and I would like to especially thank ICTS for giving us all the opportunity to be here and having this nice interaction. Thank you. Yes, to the bridge, okay? So, yeah. That's a very good question. So, yes, so I forgot your name, I'm sorry. Ravi, yes. Ravi is asking is that if indeed there is localization of exciton on a specific thiophene bridge, then what is this idea of delocalized excitation? Well, I have not stated that it is only localized on the thiophene bridge. What I want to say, to looking at the Raman intensities, is there's quite a bit of movement in this backbone. So initially, all these polymers have disjointed chains. They behave like disjointed chains with small amount of conjugated planarity involved in these. But now these disjointed chains, after getting excited, can planarize and lead to longer conjugation. What we see here is essentially some bit of this bridge doing that planarization and letting the exciton also localize on the bridge. Okay, so there is no such no such challenge. We don't challenge the concept of delocalized exciton. An exciton is a delocalized over maybe 2 or 3 monomer units. But what we are saying is the contribution of the localization and different parts has changed in the excited state. And thiophene ring is a major player in localizing it in certain parts. After that delocalization localizes, then it moves across the different chains in as energy transfer proceeds. Yes, yes. Electron. Okay, okay. No. Right, right, right. There are two different problems. An electron mobility is a different problem than exciton mobility. Okay? So an electron mobility deals with the fact that I am hopping my electron from one system to another, or it could be a coherent process, as you say. And that does not involve an interaction with the parent hole. Okay? In the case of the exciton, it is a quasi-particle with the hole and the electron wave functions involved both while the energy is getting transferred. Now, when you push in that much of energy in the polymer backbone, you have a chance of coherent transport of excitons, okay, to your interface, because you can, through your pulses, you can do that. Okay, you create a coherent population that would migrate. For the electron to have a coherence, that I don't know how you would relate, because there is dephasing of this coherence at certain time, and when you separate, I don't know how you will maintain the phases of all the electrons that are separating. But I have not really gone through that literature, but at least in the exciton migration, there is a proof that there is coherence involved. Yeah. Yeah. Yes. From the semiconductor physics. Yes. Yes. Right. No, I don't know about that for the conjugated polymer. You probably will know better. But this is what. Yes, no, I agree, but this polymer that we are evaluating is your polymer, and it shows a much longer lifetime. We are still trying to appreciate that, but the point here is that most of the polymers that you also make, you have a short lifetime of 30 picosecond. You're not changing that much now with your side chain or whatever. So yes. No. So the question is, how are you reducing the band gap? If you are reducing it through charge transfer interaction, I would say that the design is critical bit of the torsional angles. Okay. So as Mahesh pointed out, in small molecule systems, if you have a tilted orientation of the donor acceptor, in some way you can block the recombination. So these ideas are still valid for the polymeric backbone. So that has to be thought of. If you had designing based, you're reducing the band gap through charge transfer, you need to think of ways to also have similar kinds of ways to stop the recombination. Yeah, yeah. That's right. That's right. Aggregation. Yes, we tried. We tried. We didn't see any of these effects. The reason is we actually flow the system. Okay, so we don't. Yes, so we absolutely avoid photo damage. We do it under nitrogen in flow. So these are some of the critical checks we had to maintain. Yeah.